Inspecting the Main Electrical Panel Board During a Home Inspection by Nick Gromicko, Ben Gromicko, Lon Henderson, James Crum, and Robert Meyer. In this inspection article, we will learn about inspecting the main electrical panel board, from the utility service to the breakers, including common components of the panel board, and an inspection checklist. Let's begin with InterNACHI's Home Inspection Standards of Practice. Home Inspection Standards of Practice. According to the InterNACHI Home Inspection Standards of Practice, found at nachi.org/SOP, the inspector is required to inspect the service entrance conductors, the main service disconnect, panel boards, overcurrent protective devices, including circuit breakers and fuses, and service grounding and bonding. The home inspector is not required to remove panel board cabinet covers or dead fronts. You can read a short article about exceeding the standards of practice at nachi.org/exceed-or-not-exceed. Stay safe. Stay safe during a home inspection. Do not endanger yourself or others. Use personal protective equipment. You can take InterNACHI's free online Safe Practices for the Home Inspector course at nachi.org/safety_course. Electric service. Electric service is a general term used to refer to all electric service conductors and equipment. The service begins at the load end of the service drop or lateral and ends at the panel board cabinet that houses the main disconnecting means. Power from the utility company is typically delivered through 3 large conductors, which may enter the house overhead or underground. Overhead service wires are called the service drop. The service drop runs to a weatherhead at the top of a length of rigid conduit called the service mast. A typical 3-wire service drop consists of 2 insulated hot conductors wrapped around a bare, stranded aluminum wire with an internal seal, messenger cable. The bare aluminum wire also serves as a neutral. Whether it arrives overhead or underground, a neutral conductor originates as a center tap for the secondary winding of the utility transformer that supplies power to a 3-wire, single-phase, 120-240-volt system. The 2 ends of the secondary winding are the ungrounded conductors, and the midpoint of that winding is the neutral point from which the neutral conductor originates. This neutral conductor serves as the common return conductor for the 2 ungrounded conductors. The neutral conductor is always a grounded conductor, but a grounded conductor is not always a neutral conductor. This sounds confusing, but the only grounded conductor is the neutral conductor. Most people refer to all grounded conductors in branch circuits in a dwelling as neutral conductors because they all connect to the grounded neutral conductor in the service, although the code refers to them as grounded conductors. When run underground from the utility pole to the electric meter, service conductors are installed in a buried conduit or run as the underground service entrance cable. Each main service hot wire terminates at a breaker or fuse in the main disconnect, which is the first means of overcurrent protection. The main 240-volt disconnect is housed either in the panel board or in its own separate box installed in combination with or near the meter base. The main service grounded neutral conductor connects to the neutral bus bar. The location of the neutral bus bar varies depending on the panel manufacturer. It is a silver-colored bar with many small holes and screws and 1 larger hole for the main service grounded neutral wire. Next, let's learn about the meter base. The meter base is where the utility mounts its meter into the meter socket. Meter bases can be configured with the panel board location in several ways. The main disconnect can be installed at either the meter base or the breaker panel. A common arrangement may be where a meter base is only on the outside of the house and the service entrance conductors are run to the meter base and continue to a panel board inside the house. This panel inside the house may be called in common usage, but not in code, a main breaker panel, because the main breaker or main disconnect is installed in or is part of the panel board, integrated, along with the final branch circuit overcurrent protective devices, or breakers. Another arrangement of service equipment is where the meter base and main disconnect are located outside of the house and the panel board is separate. The conductors that run from the main disconnect to the distribution panel are the feeder conductors. A feeder is usually a large set of conductors run in cable or in a raceway from the service equipment to the main panel board or to a sub-panel, which has the final branch circuit overcurrent devices. Let's learn about the service entrance cable. Service entrance, or SE cables, are used for services. SER and SEU are two common types of SE cables. Type SE, style SEU service entrance cable is primarily used to convey power from the service drop to the meter base and from the meter base to the distribution panel board when the main disconnect is installed at the main panel board. SEU is an unarmored service electrical 3-wire cable with 2 conductors and a neutral. SEU typically has an oval shape because the stranded neutral conductor wraps around the cable to create an oval shape. SEU cable has a neutral conductor but does not have a grounding conductor. Since neutral conductors and grounding conductors are connected at the point of service disconnect, SEU cables can only be used up to the service disconnect to avoid significant safety concerns. SER is a round service electrical 4-wire cable that typically has up to 4 conductors and a bar neutral. The cable is designed to be used in feeder panels and branch circuits. SER cables are equipped with neutral and grounding conductors, which makes them perfect for use after the service disconnect. Panel board and cabinet. A cabinet is an enclosure or box. The panel board contains bus bars, terminals, overcurrent protection devices, and mounting hardware designed to be enclosed in a cabinet. In residential wiring, the panel board is usually not distinguished as a separate piece of equipment from its cabinet because it is normally installed inside the cabinet enclosure at the factory. Most panel boards used in 1- and 2-family dwellings come from the manufacturer already installed in a cabinet. In this article, we use the word panel board to refer to both the panel board and its cabinet. Many inspectors, contractors, and electricians refer to the panel board and cabinet together as the panel, breaker box, or breaker panel, and they do not necessarily distinguish between the cabinet and the panel board. For simplicity, home inspectors could use the term panel board to refer to the cabinet and panel board as a unit. Working space and clearance. Adequate space should be provided around the electrical panel board for safe access to the components. Please refer to the InterNACHI illustration for panel board working space and clearances found in this article online. Generally, the working space in front of the panel board must be at least 36 inches. The working space must be at least 30 inches wide in front of the electrical panel board and at least 6.5 feet in height. Panel boards must not be located in bathrooms, toilet rooms, clothes closets, or over the steps of a stairway. The overcurrent devices must be readily accessible. Illumination. Artificial illumination must be provided for the panel board working space. Dead front. The door or cover of the panel board cabinet is called the dead front. The dead front of a panel board cabinet protects a person from live parts within the panel board. According to the InterNACHI Home Inspection Standards of Practice, the home inspector is not required to remove the panel board cabinet cover or dead front. Panel board basics. Let's learn about the basic components of a panel board, including service entrance conductors, main lugs, main disconnect, branch circuits, hot bus bars, neutral bus bars, and ground bars. For a commonly installed 200 amp service, the SEU service entrance cable between the meter base and the main electrical panel board will have 2 4-aught aluminum conductors for the hots and a bare 2-aught aluminum ground or neutral conductor. The main lugs or terminals are the main connection point between incoming electricity and the panel that distributes the power to the house. At a service panel with an integral disconnect, The service conductors are attached to the lugs or terminals at the main service disconnect. Each ungrounded, hot conductor terminates at a breaker or fuse in the main disconnect, which is the first means of overcurrent protection. The main service disconnect is housed either in the distribution panel or in its own separate box. The main disconnect is a large 240-volt circuit breaker located at the top of the panel board. It controls all the power entering the home and connects to both hot bus bars running down vertically through the panel board. If the electric service utility is connected, these main terminals will be live even if the main breaker is turned off. The bare, stranded, grounded, neutral conductor connects to the neutral bus bar. The location of the neutral bus bar varies depending on the panel manufacturer, but it is always separate from the two hot bus bars. The neutral bus bars are long aluminum bars containing many holes and terminal screws to which ground and neutral branch circuit wires are attached, and there's one larger hole for the main service grounded neutral conductor. All connections should be secured with the use of a torque wrench. The service entrance conductors at the connection point with the main terminals or lugs may be coated with antioxidant according to the manufacturer's recommendations or the local code. Panel boards manufactured since the late 1940s are approved for aluminum terminations and do not require antioxidant paste on the terminations. Home inspectors may observe antioxidant applied, but it is not required. Main disconnect. The main service disconnect, the main disconnect breaker, is the master switch for the panel board. It shuts off the power to everything downstream, including the hot bus bars and all breakers mounted to them. All electricity entering a house goes through the main breaker. In an emergency, this main disconnect can be turned off to turn off all power to the house. The main breaker is the primary overcurrent protection device for the electrical system and is rated accordingly. The main service disconnect or the main disconnect breaker is usually attached or mounted to the house either inside or outside the building and is located nearest the point of entrance of the service conductors. The main service disconnect must not be installed in a bathroom. Wherever it's installed, the center of the grip of the main disconnect must be readily accessible and no higher than 6 feet 7 inches above the floor, ground, or working platform. The rating should be stamped on the breaker handle. Metal bus bars run from the main breaker down the middle of the panel board to distribute power to the various branch circuits through circuit breakers. 6 disconnect rule. A person must be able to turn off all the power to a house with at most 6 motions of the hand while at one location. Each panel board should have only one disconnecting means, and the maximum number of disconnects should not exceed 6. For new construction, the main breaker or breakers is usually located in one panel board cabinet. The multiple service disconnecting means should be grouped together and marked. Most electric services will have a single main service disconnecting means located either outdoors on the load end of the meter or in an indoor panel board. Hot bus bars. The hot bus bars are metal bars typically made of aluminum or copper, mounted to the panel on plastic insulators, and have tabs that connect with and channel electricity to the clips on the back of the branch circuit breakers. Each of the 2 conductors feeds one side of the hot bus bar section. Neutral bus bars. The neutral bus bars are typically strips of aluminum bored with holes to secure and connect wires, acting as a hub for the neutral wires returning from each circuit in the panel board, completing the loop of electricity. Some panels may have just one neutral bus bar. Grounding bars. The grounding bars are the central safety hub for the panel and the ground wires for circuits connected to the panel. They create a direct path for errant power to be discharged safely to the earth. The main electric service panel board with an integral main breaker disconnect will be the only point in the electrical system where the ground and neutral bus bars will be combined, bonded, and connected together with the grounding wires and neutral wires also bonded together. Additional distribution panel boards or subpanels will have grounds and neutrals separated. Branch circuits. A branch circuit is a general term that includes the conductors that run between the final overcurrent protective device in the panel board and an outlet such as a receptacle outlet or a lighting fixture. This term helps distinguish a branch circuit from a feeder, which supplies power to the final overcurrent devices. The branch circuit wiring enters the panel board cabinet through cable clamps installed in the knockouts. Several kinds of clamps are available, including metal and plastic. The lock nuts on the clamps should be tightly secured. Main bonding jumper, or MBJ. At the main service panel board, the two underground or hot service conductors from the meter base attach to lugs or terminals at the main breaker. The incoming grounded neutral service conductor attaches to the main lug of the neutral bus bar. In a typical electric service panel board, the neutral bus bars are bonded to the service panel board enclosure by means of a special bonding screw or strap provided by the equipment manufacturer. That component is called the main bonding jumper, or MBJ. We use the term jumper, but the main bonding jumper, or MBJ, could actually be a wire, strap, bus bar, or self-tapping screw. If it's a screw, it's usually green in color to clearly show its purpose. The MBJ should not be spliced. The MBJ is the primary connection between the grounded circuit conductor and the equipment grounding conductor, commonly called ground wires where the conductors are usually bare copper or green insulated wire, or the service equipment or supply side bonding jumper, or both at the service. The MBJ connects the service neutral wiring to the grounding electrode conductor, or GEC, and also to the service panel board cabinet. The MBJ is a reliable conductor that ensures the electrical conductivity between the metal parts required to be electrically connected. The factory-supplied bonding jumper screw or strap is shipped disconnected or as a loose component because the manufacturer doesn't know how the panel will be used. If it is used as a service equipment, main electric service panel board, the neutral conductor bus must be bonded to the enclosure. If it is not used as service equipment, the neutral or grounded conductor bus must be electrically isolated or separated from the enclosure. In the service equipment, and only in the service equipment, at the location of the main disconnect, the grounded service conductor is connected to the same neutral bus bar as the equipment grounding conductors, commonly called ground wires, and possibly one or more grounding electrode conductors. Therefore, the neutral bus bar can function as a main bonding jumper because it is the connection between the grounded service conductor and the equipment grounding conductors. In the main service panel board, the equipment grounding conductors, commonly called ground wires, attach to the grounding conductor terminal bar, which is bonded to the metal panel board cabinet by the main bonding jumper, or MBJ. Attached to the grounding conductor terminal bar in the service panel board is a large, sometimes bare or green copper ground wire called the grounding electrode conductor, or GEC, that clamps to a grounding electrode, such as a grounding rod driven into the earth, or an OOFER grounding electrode, a 20-foot length of steel rebar or heavy copper wire placed in the building foundation prior to pouring. If there's a ground fault in the house, the MBJ ensures the current can be safely directed to the ground, away from the house and the people inside. The MBJ provides low impedance fault current path back to the power supply to facilitate the tripping of the overcurrent device in case of a ground fault. Grounding is the single most important component of a building's electrical system, and the MBJ is the single most important connection in the entire electrical system. At the main disconnect, all neutrals and grounding wires are combined together and connected or bonded to the panel cabinet. If the MBJ is the green screw, it should be screwed down with little to no threaded shaft showing. On some older panels, the MBJ screw is not green and may take additional observation to recognize it. In additional panels or sub-panels, the neutrals and grounding wires are not combined and the green screw, if present, should not be screwed down. Bonding. At the main service panel board that has the initial main disconnect, neutral conductors, equipment grounding conductors, the metal service panel board cabinet, and the grounding electrode system must be bonded together. The code requires that grounds and neutrals be kept separate except at the main disconnect or the main breaker. If the electric service system has its primary main breaker outside at the meter base, the neutral and ground would be bonded only at that point, not at the breaker panel. When the main disconnect is located at the meter base, the ground and neutral terminal bars must be separate and not connected, and the main bonding jumper must be removed or disconnected. To distinguish between the ground and neutral bus bars on a panel board, an inspector can look closely at their connections to the body enclosure or box of the panel board. Ground terminal bars are screwed directly into the metal body of the panel. Neutral terminal bars are insulated from the panel body. Bonding piping. The metal gas and water piping in the house must be connected to the ground bar in the panel board. This connection is called bonding. The wire making the connection is called a bonding jumper. We bond pipes because if a metal pipe is energized inadvertently, the bonding jumper provides an easy path back to the source so that enough current flows to trip the breaker. Inspectors should check for a bonding jumper wire that crosses over the water meter. Inspectors may observe metal water lines bonded at the water heater supply pipe and metal gas pipe that are as close to the panel board as possible. For a 200 amp service, the code calls for at least 6-gauge copper to bond metal gas pipes and 4-gauge copper for water pipes. Panel board size. Panel boards, or breaker panels, are measured by their maximum current carrying capacity given in amps and by the number of circuit breakers they can hold. Code requires services to be at least 100 amperes for homes. Generally, for most homes smaller than 3,500 square feet that are not heated electrically, a 200 amp panel with 40 breaker spaces provides enough power with some room for expansion. Mounting. Panel boards should be mounted as close to where the service entrance cable enters the house as possible. When the panel board is mounted in a basement, the panel board may be observed attached to a piece of plywood. The wood provides a flat, reliable surface for mounting the box and stapling the cables within 12 inches of the box or as the local code requires. Common service equipment layout. A common layout and configuration of the service equipment may be such that the meter is on the outside of the house and the main disconnect is installed at the panel board inside the house. In this situation, the service entrance conductors would run from the weatherhead down in raceway or cable to the main disconnect. Where the meter is in the same box or enclosure as the main disconnect, the service entrance conductors would run from the weatherhead down in raceway or cable to the meter main disconnect enclosure. The neutrals should not touch the grounds anywhere in the house except here at the main disconnect panel board. This is a safety feature that provides a separate path to the ground from the neutral conductor. The ground wires of the individual branch circuits can all be connected to the same grounding bar in the main panel. The ground wires carry the ground to each and every device, fixture, and appliance in the house. At the main service disconnect panel board, the two hot cables from the meter base attach to lugs or terminals on the main breaker. The incoming neutral cable attaches to the main lug of the neutral grounding terminal bus bar. In the main service panel board, neutral grounding terminal buses must be connected together, usually by a wire or metal bar called the main bonding jumper. In sub-panels and all other locations downstream from the main service panel, the ground and neutral components must be electrically isolated from each other. Now let's look at the sub-panel. Sub-panel or additional distribution panel board. A new panel board should not exceed 80% of its full capacity, which means that it should have open slots for future additional circuits. However, an older panel board may not have room for additional circuits, and a sub-panel may be added. Sub-panels or additional distribution panel boards are typically powered by a double pole breaker in the main service panel board with a 4-wire SER feeder cable that carries 2 hots, 1 ground, and 1 neutral conductor. In a sub-panel, neutrals and ground wires are kept separate and are terminated into separate bars. The tie bar at the bottom of the panel board must be removed in order to separate the neutral bus bar and the grounding terminal bus bar. Only the grounding bar is bonded to the panel's enclosure using the main bonding jumper. At a sub-panel, branch circuit ground and neutral wires are connected into separate bus bars. They should not be connected to the same bus bar the way they are at the main disconnect. This is a common wiring mistake. A sub-panel must be equipped with separate ground and neutral bars, but only the ground bar should be bonded to the panel enclosure. Sub-panels, or additional distribution panel boards, cannot have the grounded conductors or neutrals and the equipment grounding conductors, or bare grounding wires, terminated together. The grounded conductors and the grounding wires must be separated in a sub-panel. The grounded conductors cannot be bonded to the panelboard cabinet. A 4-wire SER feeder cable should run from a 240-volt double pole breaker in the main panelboard to the sub-panel. 2 ungrounded conductors, or HOTs, 1 grounded conductor, or neutral, and 1 grounding conductor, a bare ground wire. Prior to 2008, the grounding conductor was not required at detached buildings. Terminating the neutrals and grounding wires together with a grounding electrode conductor, or GEC, at that location was done at detached buildings like barns, shops, or garages, but never for sub-panels in the same structure. There are exceptions, such as livestock buildings. Grounding wire. The equipment grounding wire, or EGC, may be commonly referred to as the grounded conductor, grounding conductor, or grounding wire. The equipment grounding conductor is the green or bare copper wire. It is not intended to carry current except in case of a ground fault. Neutral wire. The grounded conductor of the service, feeder, or branch circuits is commonly called the neutral. It is required to be white or gray. Neutral is used interchangeably with grounded conductor. The grounded service conductor is what we call the neutral, a current-carrying conductor. Many inspectors refer to all grounded conductors, the white wires in branch circuits, as neutral conductors or neutrals because they all connect to the grounded neutral conductor in the service. Hot wire. The ungrounded conductors are typically referred to as the hot conductor, a current-carrying conductor. Grounding electrode. A grounding rod, footing reinforcing steel, and metal underground water pipes are examples of grounding electrodes, which are metal, electrically conductive terminals through which current enters the earth. There are several methods of connecting the grounding system to the ground, with a driven grounding rod being the most common in most areas. Most residential construction requires 2 separate grounding electrodes in any combination of the following, which need to be at least 6 feet apart. Driven rods, or rod-type grounding electrode rods, metal water pipes, well casings, OOFR grounds, ground plates, steel framing, and ground rings. Historically, the grounding system had just one connection to ground, and this was nearly always made on the water supply pipe. However, 2 connections are now required by most jurisdictions to ensure a low impedance ground, or one with little resistance. Because most utility companies now install plastic portable water supply levels, a water pipe cannot be used as a grounding means, so one of the other electrodes previously listed must be used. It is also important to note that all electrodes that are present in the dwelling must be bonded together to form a single and complete grounding electrode system. Gas piping should not be used as a grounding electrode for safety reasons, but in most areas, gas lines are required to be bonded to the grounding system if they are likely to become energized. Grounding electrode conductor, or GEC. The GEC is a conductor that connects the system grounded conductor or the equipment to a grounding electrode or to a point on the grounding electrode system. The GEC is copper, aluminum, or copper-clad aluminum. It is not intended to carry current except in case of a ground fault. It can be bare and without color. The GEC is usually connected to the grounded service conductor, or neutral service conductor, in the service equipment where the main disconnect is located or in the master enclosure. The grounding electrode conductor, or GEC, and the grounded service conductor are bonded together to the metal service enclosure by the main bonding jumper, a screw or jumper connecting the neutral bus bar to the cabinet enclosure. The equipment grounding conductors, the grounding wires, are also brought to this point and tied to the ground service conductor, the neutral conductor, and to the grounding electroconductor, or GEC. The other end of the grounding electrode conductor, or GEC, is connected to one or more grounding electrodes, such as an underground water pipe and grounding rod. Rod and pipe electrodes must be at least 8 feet in length to be considered a grounding electrode. The rod and pipe electrodes must be installed at least 8 feet of length in direct contact with the soil in the ground. No part of any grounding electrode can be closer than 6 feet to any other. The upper end of the electrode should be flush with the ground or just below the ground surface so that the end and attachment are protected from damage. If you find a rod sticking up out of the ground more than just a couple of inches, that's a defect. It should be at or just below the soil surface. Double-tapped breakers. Home inspectors sometimes refer to double-tapped breakers as double-lugged breakers. Most circuit breakers are designed to accept only one wire. For those breakers, there can only be one wire under the screw or lug. 2 or more wires should not be twisted together and placed under the screw. The primary reason double lugging or double tapping is not permitted is that the connection is not designed for 2 wires, and because of this, one or both wires may not be securely installed. This insecure installation of more than one wire at the breaker could lead to a disconnected circuit or micro-arcing that could damage the wire and breaker. 2 heavily used circuits installed on the same breaker might cause overheating at the breaker or cause the breaker to trip excessively. Some breakers, such as square D QO breakers, are designed to accommodate 2 wires. Typically, these will have a loose plate under the screw with 2 slots or grooves for each wire end. 2 conductors that are sized according to the chart on the side of the breaker are inserted on either side of the screw. The screw tightens the plate down, securing the wire ends. An electrician or trained inspector can determine if 2 circuits on the same breaker are permitted. Double-tapped neutrals. The grounded conductors, commonly called neutrals, are the white wires inside a residential electrical panel board. Only one neutral wire is permitted to be connected under one lug of the neutral bus bar. Panelboard neutral bus bars are usually not listed for use with more than one wire per terminal. This rule can be thought of as the 1 wire per hole rule. Neutral wires should not be doubled or tripled lugged under a lug or fastener of the neutral bus bar. Neutrals should not be combined with a grounding wire, bare copper or green wire, either. There are several reasons that neutral wires should not be double lugged at the neutral bus bar, including the connections at the neutral bus bar are designed to accommodate 1 wire. 2 wires might not be securely terminated. 1 wire might lose its connection. The circuits cannot be readily isolated if electrical work is being done on one of the circuits. It is sometimes said that double-lugged neutrals were not prohibited by the National Electrical Code, or NEC, until 2002. This is an incorrect interpretation of the NEC. Until 2002, the NEC simply stated that panel boards must be installed according to Underwriters Laboratory, or UL 67. UL 67 states, quote, "An individual terminal shall be provided for the connection of each branch circuit neutral conductor," unquote. The NEC has never allowed double-lugging neutrals, even if it did not specifically address the topic until 2002. Incorrect wire size for a breaker. An incorrect wire size or gauge is a common observation by a home inspector when inspecting 15 and 20 amp breakers at the electrical panel board. An incorrect wire gauge may be found at any breaker. An example of an incorrect wire gauge is where a 14 gauge wire is connected to a 20 amp breaker. This is a defect because the size of the breaker, 20 amp, is too big for the size of the wire, 14 gauge. A 14 gauge wire is the minimum size for a 15 amp breaker. The size of the wire connected to the 15 amp breaker is permitted to be bigger. To put it another way, a 15 amp breaker is the biggest size breaker for a 14 gauge wire. They are commonly found to be correctly connected to each other, a 15 amp breaker and a 14 gauge wire. A 12-gauge wire is the minimum size for a 20-amp breaker. The wire gauge is permitted to be bigger than 12-gauge when connected to a 20-amp breaker. A 10-gauge wire is the minimum for 30-amp breakers. You can't have a wire smaller than 10-gauge when it is connected to a 30-amp breaker. A wire gauge that is smaller than the minimum size for the breaker is vulnerable to overheating. Oversizing the wire for the breaker is allowed. If the bare wire end is visible, a home inspector may be able to observe and determine the wire gauge, but just seeing only the insulated wire can make identification more difficult. A home inspector should never insert a potentially conductive instrument into the electrical panel in order to take a measurement of the wire gauge. If an inspector uses a wire gauge measurement device, it must be tested and confirmed to be non-conductive. Different manufacturers have different thicknesses of the plasticized insulation on the wire, which may make an inspector look for other clues to the wire gauge, particularly the labeling on the wire itself. Table E3705.5.3 of the 2021 IRC, often referenced alongside NEC, National Electrical Code Section 240.4D, pertains to the overcurrent protection ratings for specific types of conductors in residential applications. This table is crucial for home inspectors as it assists in determining whether the overcurrent protection devices, like circuit breakers or fuses, are correctly sized for the conductors they protect. You can reference this table in our online article, Inspecting the Main Electrical Panel Board During a Home Inspection, found at nachi.org/inspect-main-electric-panelboard.htm. The main intent of the NEC 240.4D is to provide standard overcurrent protection for conductors to prevent them from carrying more current than they are rated for, which could lead to overheating and potentially cause a fire hazard. The NEC has established maximum overcurrent protection ratings for certain conductor sizes, and this table translates these limitations into a format that can be easily followed during inspections. Here's a simplified explanation of what the table includes. Conductor size. This column lists the sizes of the conductors, usually in American wire gauge or AWG or KC mil. Conductor size is a critical factor in determining the appropriate overcurrent protection. Copper conductors. Since copper is the most common conductive material used for electrical wiring, this column will specify the maximum overcurrent protection rating for copper conductors of different sizes. Aluminum or copper-clad aluminum conductors. This column addresses the maximum overcurrent protection rating for aluminum or copper-clad aluminum conductors, which have different properties than pure copper conductors and therefore require different considerations for overcurrent protection. Home inspectors can use this table to check that each circuit has the appropriate size breaker or fuse. If, for example, a 12-gauge copper wire is protected by a 30-ampere breaker, this would be a defect, since the table indicates that the maximum overcurrent protection for a 12-gauge copper conductor is 20 amperes. Exceeding this limit could cause the conductor to overheat under overload conditions. For home inspectors, knowledge of the specifics in these tables is helpful for educating homeowners on the safety aspects of their electrical system, including the various types of wiring commonly installed in homes. The AC breaker size. If a home inspector is checking the panelboard circuit breaker for the air conditioning or heat pump unit and it appears to be oversized in relation to the size of the wire, the inspector may make the mistake of calling it a defect when it is not. This situation is a common source of confusion because the equipment label will sometimes allow the rating of the overcurrent protective device to exceed the ampacity of the circuit conductors. The International Residential Code, or IRC, and the National Electric Code, or NEC, provide an exception to the general rule for overcurrent protection ratings of breakers and the connected wire sizes. The commonly known maximum overcurrent protection rules for breakers in relation to the wire size do not apply to air conditioners and heat pumps. For example, if a home inspector observes a 50-amp AC breaker on an 8-gauge wire, that may not be a defect. It might be okay and likely not a defect, even though the breaker will be sized larger than what the inspector thinks is permitted. For example, if a home inspector observes a 50 amp AC breaker on an 8-gauge wire, that may not be a defect. It might be okay and likely not a defect even though the breaker will be sized larger than what the inspector thinks is permitted. The home inspector should know that the International Residential Code, or IRC, and the National Electric Code, or NEC, provide exceptions to the general rule for overcurrent protection ratings of breakers and the connected wire sizes that are for only air conditioning and heat pump equipment. Branch circuits for the air conditioning equipment and big motors may have an overcurrent protection device rating that exceeds the conductor ampacity, and this is not a defect or an electrical violation. In the 2021 IRC section E3705.5.4, it says that the air conditioning and heat pump equipment circuit conductors are permitted to be protected against overcurrent in accordance with section E3702.11, which says that the branch circuit overcurrent device rating must be the size and type marked on the appliance. To determine the maximum size of the overcurrent protective device and the minimum size of the conductors for the air conditioning and heat pump equipment, the inspector has to use the data on the equipment nameplate attached to the unit outside. The overcurrent protective device rating for the air conditioning condensing unit and heat pump circuits is stated on the equipment nameplate, with a minimum and maximum rating given. The nameplate will also state the minimum circuit ampacity for the branch circuit conductors. The home inspector should know that the IRC and NEC provide an exception to the general rule for overcurrent protection ratings of breakers and the connected wire sizes. And knowing that exception and applying it will help home inspectors do better inspections. Read more about inspecting oversized AC breakers by visiting www.nachi.org/inspect-oversized-air-conditioning-small-gauge-wires. Safety issues with panel boards, such as Federal Pacific Electric. There's a general consensus among electricians and many industry experts that some electrical panels have significant safety issues. Federal Pacific Electric, or FPE, stab lock panels, Zinsco, GTE Sylvana, Bulldog Pushmatic, and Challenger distribution panel boards are the most commonly encountered among these problematic panels. The recommendation for these panels is to replace the electrical panel board. There are no recalls on these panel boards, with the exception of approximately 1,000 Eaton Cutter hammer panels in 2014 that were built on the Challenger design. Home inspectors may receive criticism from unhappy sellers and even from some electricians about the need to replace these panels. Two common arguments against replacement are, "It's working just fine," or "the old breakers can be replaced with new aftermarket breakers." No one can know if it's working just fine until it's under stress. One of the significant issues with FPE, Zinsco, and Bulldog panels is that the breakers fail to trip with overcurrent, shorts, or ground faults at rates far higher than industry standards. In actual testing, breakers in these panels may trip correctly a few times before failing. Other issues with these panels are that breakers can fatigue over time, become loose on their buses, lose connection, overheat, and even melt. Most, if not all, aftermarket replacement breakers are not UL approved and cannot be considered reliable. Some aftermarket breakers are incompatible despite their advertising, such as aftermarket Pushmatic breakers. Using other branded breakers that may fit the buses is not an approved repair or considered safe. Complete panel board replacement with the most modern equipment remains the best recommendation. Note that in most areas, replacement panel boards are not required to meet all of the latest code requirements. If there is a need to modify or extend the old breaker panel to include modern AFCI breakers, the old panel boards may not be able to accommodate them. A home inspector should know what the local community or state requires. Split bus panel. Between the 1950s and mid-1980s, split bus panels were installed in many homes. These panels do not have a main breaker or one main disconnect. They have two bus sections. Typically, the upper bus has double-poled 240-volt breakers, including one that feeds the lower bus section where the majority of 120-volt breakers are installed. The upper bus section should not have more than 6 separate breakers or breaker handles. Breakers that have handle ties that cause both handles or toggles to move together are considered one throw. The NEC requires no more than 6 breakers, or throws, to completely turn off the power to a panel and home. This is called the 6 throws rule, which means that no more than 6 hand motions will turn off the whole panel. An inspector should never see more than 6 breakers to turn off a panel. As of the 2020 NEC, services must have one main disconnecting means. While split bus panels are an obsolete design, they still may be operational during the time of the home inspection. There is no requirement to replace existing split bus panel boards. Allowed to install 120-volt breakers on top, 240-volt portion of the panel. When home inspectors see a split bus panel, they should count how many throws are required to turn off the panel. More than 6 throws are usually found where someone has added a circuit to a full panel by adding a double breaker, tandem or piggyback breaker, on the upper bus section. Installing an additional 120-volt breaker in the top portion of a split bus panel is likely a defect. The breaker may not be listed or approved for that panel. This changes the number of disconnecting throws from 6 to 7, and that's a defect. Circuit identification. The 2021 IRC Section E3706.2 describes the panel board circuit identification requirements. All circuits should be identified with their clear, evident, and specific purpose. Each circuit should be distinguishable from all others. Spare circuits should be labeled accordingly. There should be a circuit directory installed on the face of the panel board door, inside the panel door, or in a location adjacent to the panel door. The circuit labeling should be permanent and legible. Homeowners and contractors should use factory-made panel labeling kits. This requirement helps protect occupants and contractors from injury that could result from shutting off or turning on the wrong circuit breakers. Home inspectors may often find the panel board door with illegible markings that fail to identify the circuits specifically and accurately. Each circuit must be detailed enough to distinguish it from all other circuits. Labeling a dozen breakers with plugs, lights, or Ben's room cannot distinguish each circuit from all the others. If the markings at the breakers of a panel board are not legible, a code violation exists, and that condition is a defect that needs correction. A potential hazard exists where circuit breakers are mislabeled or ambiguously labeled because the occupants or electrical workers might not actually be turning on what they intend to turn off. Because this is a safety issue, panel directories must be labeled plainly with words that provide complete and accurate descriptions of the circuits served by each overcurrent device. Contamination. Electrical components must be protected after they are installed. The 2021 IRC Section E3404.7 refers to the integrity of electrical equipment. The internal parts of electrical equipment, including bus bars, wiring terminals, insulators, and other surfaces should not be damaged or contaminated by foreign materials such as paint, plaster, cleaners, or abrasives, and corrosive residues. For example, a newly installed panel board should be covered when the electrical contractor is installing the rough wiring above the electrical panel board. Otherwise, the unprotected panel board and its components could be covered with dust and debris. Another example could be when the panel board is installed and the drywall contractor uses a router to cut openings for electrical boxes or fixtures. The drywall dust could enter the uncovered panel board. Another example of an unprotected panel board could be when the bus bars might be coated with paint while the walls were being spray painted. There should not be any paint or wall texture sprayed on the wiring, connections, and buses inside an electrical panel. The general interpretation is that any contaminant that cannot be removed with a dry cloth is not allowed. Coordination between construction trades is needed to prevent these types of problems and is required by the code. Nests from pests such as bees or mice should be reported as in need of correction. Foreign debris of all types should be removed from equipment. There should not be any damage to components of the electrical panel board, inside and out, that might adversely affect its safe operation or the mechanical strength of the equipment. Parts of the panel board and its components that are broken, bent, cut, or deteriorated by corrosion, chemical action, or overheating are all defects that should be reported as in need of correction. Knockouts and connectors. According to the InterNACHI standards of practice, the inspector must report any unused circuit breaker panel opening that was not filled in need of correction. The 2021 IRC section E3404.6 refers to unused openings in electrical equipment, including the panel board. Unused openings at the panel board, other than openings for mounting purposes or special equipment, should be closed to provide protection equivalent to the cabinet wall of the equipment. This includes cabinet and enclosure concentric and eccentric knockouts and circuit breaker knockouts in panel board covers. The panel board enclosure is designed to keep out foreign objects, protect the conductors and breakers, contain arcing resulting from faults in closure, and protect persons from accidental contact with energized components. Knockouts range in size from 1/2 inch to 2.5 inches in typical residential construction, and are referred to in trade jargon as knockouts simply because a plug has to be knocked out with a tool to create an opening where a box or enclosure has been factory pre-punched. Knockouts being left open and unused in boxes and other cabinets is a very common problem. A knockout opening in a box is sometimes covered with tape, which is not equivalent to the wall of the box, and that is a defect. Unused openings must be closed with appropriate materials for the protection of the circuit conductors and devices, as well as for protection against shock by someone inserting a finger or tool into the enclosure. Listed knockout plugs are available for this purpose. Metal plugs used with non-metallic boxes will not be grounded, and recessing them 1/4 inch from the outer surface will limit contact. The idea is to help prevent inadvertent contact with an energized surface. This section is not intended to be applicable to holes provided for fasteners for mounting purposes, cooling slots, and similar openings that are part of the design of the listed equipment. In the context of this section, unused openings are openings that are drilled, punched, or knocked out of the enclosure. Handle ties. 240-volt breakers have 2 handles that must move together. There must be some device like a clip or pin that makes the 2 handles act as one or move together. Also, tandem breakers that are on a multi-wire branch circuit should have handle ties, although this has not always been required. Wire designations. Wires in a panel must be correctly designated for their use. A white wire cannot be terminated or connected to a breaker unless it is permanently marked as an ungrounded conductor, or hot. This is typically done by wrapping the white wire with black tape or marking it with a permanent black marker. Similarly, a black wire cannot be used as a neutral, white wire, without remarking it. Overheating and corrosion. An inspector should look for discolorations that may indicate a loose connection from a micro-arcing that can get the connection very hot. This can cause melted insulation on the wire or patina on the terminal. Corrosion on terminals should be reported as defective and in need of correction. Solid conductor aluminum branch circuit wiring. The InterNACHI Home Inspection Standards of Practice requires home inspectors to report the presence of solid conductor aluminum branch circuit wiring observed during the inspection. Section 3.7 of the standards states, quote, "The inspector shall report as in need of correction the presence of solid conductor aluminum branch circuit wiring, if readily visible," unquote. We suggest that the inspector report any observed wiring defects as in need of correction. The presence of solid aluminum conductors should be documented in the inspection report. In addition, solid aluminum wiring confirmed or suspected of being installed before 1972 should be recommended for evaluation by a licensed electrician. Backfeed breakers. Some panels will be supplied with power that enters through a breaker instead of being directly connected to the buses in the panel. This is backward from a more typical configuration. The breaker remains energized even if it is off or removed from the bus. Because this is dangerous, there must be a screw, clamp, or clip that permanently secures the breaker to the panel board so that it can be not simply pulled off of the bus bars. Inspectors should always look for a means to secure backfed breakers. A missing retaining device would be a defect. Surge protector. Whole house surge protectors should be installed on new panel boards. A surge protector protects the home circuits in the event of a power surge through the service conductors, such as from a lightning strike. They are frequently seen added to existing panel boards. These devices are typically connected through a dedicated 240-volt breaker. They cannot be double-tapped into an existed 240-volt breaker. There's an inspection image posted by InterNACHI member Yasadel Martin on InterNACHI's public forum, found at forum.nachi.org, of a double tap at the main disconnect terminals or lugs. The terminals are not rated for 2 conductors, especially not different sizes. There is usually an indicator LED light that indicates the proper function of the surge protector. Most surge protectors are sacrificial or single-use devices. If there is a large power surge, the surge protector dies, protecting the system, and must be replaced. If the LED is not glowing, typically green, then the surge protector should be reported as needing replacement. Multi-wire branch circuit wiring. A multi-wire branch circuit is a 3-wire circuit of 2 ungrounded conductors, hot, and a grounded neutral conductor. For example, the circuit that supplies an electric range or electric clothes dryer is a multi-wire branch circuit. The wires will be terminated on a double-pole common trip breaker that is installed in the panel board where the 2 poles are 120 volt on 2 different buses. The 2 hot wires, being on opposite buses, can share the neutral because the 2 conductors are energized at different moments in the alternating current cycles. The neutral is not sized to have a doubled return current. The 2 circuits also share the grounding wire. The red and black ungrounded conductors sharing the same neutral conductor should be grouped or tied together, typically with a cable tie or tape, except when it is obvious as to which conductors go together, like when a 3-wire NM cable enters the enclosure in a single connector. Multi-wire circuits must be supplied by a 2-pole circuit breaker or 2 single-pole circuit breakers with an approved handle tie. A nail holding the handles of 2 breakers together is not permitted and is a defect. Improper installation of cables used for multi-wire branch circuits containing 4 conductors can result in hazardous problems. Improper wiring or mishandling of multi-wire circuits can cause overloading of the grounded neutral conductor and/or destruction of equipment. Failure to properly terminate the underground hot conductors to separate phases could cause the grounded neutral conductor to become overloaded from excessive neutral current, and the insulation could be damaged or destroyed. Conductor overheating is known to decrease insulating material service life, potentially resulting in a fire from arcing faults in hidden locations. We do not know just how long conductor insulation will last, but heat does decrease its lifespan. Wiring diagram. The paper label in modern panels shows how and where the common styles of breakers can be installed. The diagram is to prevent overloading a panel board beyond its capacity. Adding more currents using tandem breakers on yokes that are designed for standard single breakers often happens with additions and basement finishes where the contractor or homeowner is trying to keep the existing electrical panel. White powder. A white powder may be observed on breakers, and this is usually observed in older panels. Some manufacturers of these breakers have explained that the white powdery residue is from a plug used in the manufacturing process that breaks down. It's a material used to keep someone from tampering with the screw. Keep in mind, it's not always white. The manufacturers claim that it is not an indicator of defective breakers and that the breakers are not damaged by it. Improperly stripped wires. The insulation on current-carrying wires should be stripped back only far enough to expose sufficient wire for the termination. The standard requires the entire cable with non-metallic sheaths to be installed with the clamp at the cabinet, which includes the sheathing. The sheath must extend at least 6 millimeters or 1/4 inch inside the cabinet and beyond any clamp. The cable should be installed in a neat and workmanlike manner, according to the NEC 393.14 installation. AFCI and GFCI breakers. Please refer to Section E3902 of the 2021 IRC that relates to GFCIs and AFCIs. An arc fault circuit interrupter, or AFCI, protects people from arc faults by recognizing characteristics unique to arcing and by de-energizing the circuit when an arc fault is detected. A ground fault circuit interrupter, or GFCI, senses any difference in current between the supply on the underground hot conductor in a circuit and the grounded or neutral conductor. If the circuitry recognizes a differential of more than 5 milliamps between supply and return, the GFCI trips open the circuit, causing all power to be disconnected. For this reason, a GFCI breaker or GFCI receptacle can protect all outlets downstream. GFCI protection is recommended for the following: 15 and 20 amp kitchen countertop receptacles and outlets for dishwashers, 15 and 20 amp bathroom and laundry receptacles, 15 and 20 amp receptacles within 6 feet of the outside edge of a sink, bathtub, or shower, electrically heated floors in bathrooms, kitchens, and hydromassage tubs, spas, and hot tubs, 15 and 20 amp exterior receptacles which must have GFCI protection except for receptacles not readily accessible that are used for temporary snow melting equipment and are on a dedicated circuit. 15 and 20 amp receptacles in garages and unfinished storage buildings, 15 and 20 amp receptacles in boathouses and 240 volt and less outlets at boat hoists, 15 and 20 amp receptacles in unfinished basements except receptacles for fire or burglar alarms, 15 and 20 amp receptacles in crawl spaces at or below ground level, and 15 and 20 amp receptacles in indoor, damp, and wet locations. The type of arc fault circuit interrupter, AFCI device currently required by the IRC and NEC is the combination type. This circuit breaker type of AFCI that mounts in the panel board at the beginning of the branch circuit or feeder provides protection for the entire branch circuit or feeder. The AFCI device consists of a standard circuit breaker with additional electronic circuitry that is capable of recognizing the unique current fluctuations that result from an arcing condition. Combination type AFCI breakers will be labeled. They may have different color test buttons from one panel board to the other. A combination type AFCI should be installed to provide protection at all branch circuits that supply 120 volt, single phase, 15 and 20 ampere outlets installed in kitchens, family rooms, dining rooms, living rooms, parlors, libraries, dens, bedrooms, sunrooms, recreation rooms, closets, hallways, laundry areas, and similar rooms or areas. Where branch circuit wiring in a residential building is modified, replaced, or extended, the branch circuit should be protected with AFCI and GFCI protection. GFCIs and AFCIs must be installed in readily accessible locations because they have test buttons that should be pushed periodically. Manufacturers recommend that homeowners and inspectors test or cycle the breakers and receptacles periodically to help ensure that the electrical components are working properly. Many manufacturers state that their devices should be tested by using the test and reset buttons on the breaker or receptacle. Electrical panel board inspection checklist. Take inspection images for every task of the inspection process. Wear personal safety protection, including glasses and gloves. Touch the panelboard cabinet and front cover with a non-contact voltage detector. Check for adequate workspace, clearances, and illumination at the panelboard. Read the label on the cabinet front cover to identify the cabinet name and type. Check the condition of the dead front cover and for proper fasteners. Check specific identification for all breakers. Check for inspection stickers and dates. Check for unused openings, including knockouts. Identify the main service disconnect and rating if labeled. Identify the breakers in the off position. Remove the dead front cover safely and carefully. This is not required. This is optional and it is hazardous. Gaps greater than 1/8 of an inch between the cabinet and wallboard are not permitted. Check for rust, corrosion, or water inside the cabinet. Foreign objects or contamination inside the cabinet are not permitted. Check service entrance conductors and main lugs. Check clamps, connectors, and bushings. Check for disconnected or loose conductors. Inspect the main bonding jumper. Inspect the grounding electrode conductor, the GEC. Locate and follow grounding and bonding components. Check the material type of the main water supply pipe. Check for damage to wires or sheathing. Check for melted or scorched conductor insulation. Check for overfusing or oversized breakers in relation to the connected wire gauge. Check for loose equipment grounding conductors. Check for doubled neutrals and doubled hot conductors. Look for multiple wires under a single screw at the neutral bus bar. Look for different gauge wires under a single screw at the grounding conductor and terminal bar. Check for solid conductor aluminum branch circuit wiring. Identify any breakers that are not permitted by the manufacturer. Check for identified handle ties. Test GFCIs and AFCIs with test buttons. Check multiple cables in connectors and clamps. A doorbell transformer inside the cabinet is not permitted. In the sub-panel, confirm that the EGCs, or equipment grounding conductors, are on a separate terminal bar that is bonded to the cabinet and that the grounded conductors, or neutrals, are isolated or floating from the cabinet. Never leave the panel board exposed. Replace the cabinet's dead front cover immediately, correctly, and safely. You can join the discussion about this inspection article by visiting our forum at forum.nachi.org/t/main-electric-main-home-inspection/2378005.